Okay, we're going to look at some tutorial problems for Chapter 2, Section 1. The first one is an old well-known result that there are arbitrarily large sets of consecutive integers containing no primes. So although there are infinitely many primes, one can find arbitrarily long strings of consecutive integers none of which are prime. The way we deal with that is by construction. So we simply take this set n, think of n as large. We take this to be n factorial plus 2, this will be divisible by 2, n factorial plus 3 will be divisible by 3, n factorial plus n factorial, which will be divisible by n which will be divisible by n. So each element of this set is going to be consecutive, and the size of the set is just going to be this number minus this one plus 1, so that's n factorial minus 1 elements. The second question is slightly more odd. We take n bigger than 1, we fix this, so think of n as 100 or something, and we take s to be, you multiply this n by 30 and add k, where k goes between 0 and 29, and you want to show that s contains at most, for any n that you've picked, contains at most 7 primes. This is one of those sort of brain teasery type problems. You might like to have a think about it before looking at the worked solution. So the solution goes something like this. Here's my set S, which consists of these numbers for k between 0 and 29. So each number of this, if we want each one of these to be prime, or if we want any of these to be prime, then k has to be one of 1, 7, 11. It can't have any factor in common with 30. So 1, 7, 11, 13, 17, 19, 23, 29. Now the trick is to read each of these modulo 7. And modulo 7, the numbers of this form for these values of k are congruent to 2n plus 1. So for example, 30n is congruent to 2n and 1's 1. Or 2n, 2n plus 4, 2n plus 6, 2n plus 3, 5, 2 and 1. Now there are 1, 2, 3, 4, 5, 6, 7 different numbers in this set, and so modulo 7, at least one of these must be 0 mod 7, and so in other words, at least one of these numbers must be divisible by 7. So out of the 8 possible cases we had here, one of the numbers of this shape for one of these values of k must be divisible by 7, and that only leaves me with then, so S contains at most 7 primes, because you started with 8 possibilities and one of the numbers is not going to be prime, so you've only got 7 possibilities left. So S contains at most 7 primes. Question 3 is rather nice problem, interesting problem here. We take m bigger than 1 and we take p1 up to ps to be all the primes less than or equal to m. And we're going to prove this little inequality here. It just says that the partial sums of 1 over n for n equals 1 up to m is less than this product. And then we're going to deduce this infinite product, 1 minus 1 over pj, where this is the jth prime. This product is 0. The infinite product has a limit of 0. So this will follow easily by just multiplying this up to here, because this product is just this one, but up to some point s. Okay, well, here's the little proof of this. So we let lambda be the set of all integers whose prime factors, are at most m, and each of these primes are less or equal to m. So we look at this product on the other side that we were given on the right hand side. And you can see each one of these factors here is going to be the limiting sum of a geometric series, and the common ratios are all less than 1, so it all converges. So I can expand this out and expand this out and so on. And by the fundamental theorem of arithmetic, when I take all the brackets out of this, I'm going to get a sum of 1 over n, where n, all the prime factors of this n, consist of these primes p1 up to ps, which themselves are factors of, these prime factors are at most m. So if the prime factors are at most m, then this sum will contain all of the reciprocals of n for n less or equal to m plus more besides. So this sum is bigger than this one. Now if we then multiply this up to the other side and rewrite the thing, we get the sum n equals 1 up to m of 1 over n multiplied by this product. So I'm multiplying the product of both sides by this infinite product, and this will turn into 1. So this is going to be less than 1. And now we know that this diverges as m goes to infinity. This diverges, so this must be converging to 0 because the product of the two has to be less than 1. And so we see then the desired result. This diverges as m goes to infinity, so the infinite product must converge to 0 as s goes to infinity.